The highly sophisticated James Webb telescope just found something new on the Trappist-1, and it may be the answer the world has been looking for about life on other planets. The Trappist-1 system is one of the most intriguing star systems that has been found in the last decade. It's 40 light-years away from Earth and lies in the constellation Aquarius. Unlike the Sun, which is a G-type sequence, the Trappist-1 is an ultra-cool dwarf. It's significantly smaller than the Sun, with its mass being only 9% of the Sun's. The same can also be said of its temperature. The Trappist-1 has a surface temperature of 2,290 degrees Celsius, or 4,160 Fahrenheit. For context, the Sun's surface temperature is 10,000 degrees Fahrenheit, or 5,600 Celsius. These characteristics all result in a lower luminosity for this star. But the one thing it may be competing with the Sun is how many planets it has in its system. The Trappist-1 has 7 planets in its rotation that are all Earth-sized. The remarkable thing about the 7 planets in this system is that they are on remarkably close orbits. Even its farthest planet, which is Trappist-1H, is closer to the star than Mercury is closer to the Sun. And mind you, Mercury is the closest planet to the Sun. But unlike Mercury, which is extremely hot because of its proximity to the Sun, the planets in the Trappist-1 system don't experience scorching hot temperatures. This is because of the star's low energy output. But do you know what is even more fascinating about the Trappist-1 system? It is 7.6 billion years old, making it significantly older than the solar system. This is enough time for life to grow on the planet, but the conditions don't seem suitable. 3 of the planets in the Trappist-1 system, Trappist-1e, Trappist-1f, and Trappist-1g, exist in the Goldilocks zone. This simply means that liquid water may be able to exist on the surfaces of these planets. Now, because of how compact and tightly packed this system is, there are certain dynamics that are at play here that can never be found in other planetary systems. For one, the gravitational interactions between the planets in the system are strong, so it creates resonance patterns that give us deeper information into their masses and densities. By paying attention to and studying these resonances, we have been able to ascertain that the planets in the system are rocky and not gas planets. Although the proximity of these planets to its host stars raises questions about their habitability, it also causes problems. But there just may be hope. Studies suggest that the planet Trappist-1e has a possibility of habitating life because it has a secondary planet. What more could be lying within this planet? To understand this planet, we must understand how its star works. Have you ever wondered why red dwarfs struggle to host habitable planets, especially in the early stage of development? Unlike the Sun, which has a stable evolution, red dwarfs experience prolonged periods of high-energy radiation in their pre-main sequence phase. During the pre-main sequence phase, the star emits high levels of ultraviolet rays and radiation, and the intensity of the radiation emitted is determined by the internal dynamics of the star. Let's take a look at the pre-main sequence phase of the Sun in comparison to that of red dwarfs. This phase is divided into 3 stages. In the first stage, which is the protostar stage, the Sun emits energy majorly through contraction and the release of gravitational energy. But for the red dwarfs, it maintains a fully convective layer throughout its entire lifetime. The turbulent plasma movement of the red dwarfs generate powerful magnetic fields, which realign and cause flares. These flares are stronger than the ones produced by the Sun. They release bursts of energy that are powerful enough to destroy planets. This would explain why the planets that are the closest to the Trappist-1 are completely inhabitable. High-energy photons that are released from the star ionize the surface of the planets that are in the star's orbit. It causes the atoms and molecules on the planets to reach escape velocity. This process is known as hydrodynamic escape and is effective at removing lighter elements like hydrogen from a planet's surface. These lighter elements are usually the primary components of primordial atmospheres formed during planetary accretion. As the planets are exposed to the constant bombardment by high-energy photons, they start to lose their elements like carbon dioxide and water. This leaves the planet barren. These issues only get worse over time because in the early stages of red dwarfs, stellar activities are prolonged. The sun gets to a point where it stabilizes and its radiation rate remains at a certain point. Right now, the sun has had a steady radiation rate of 30% for 0.4 billion years, and it is expected to remain that way for the next 5 billion years. However, this is not the case for the red dwarf. These stars experience high levels of radiation constantly for long periods, leading to the loss of the atmosphere for planets that are in close orbit. This can be clearly seen in the Trappist-1 system. Research shows that the fate of a planet depends on its component and its proximity to its host star. So if a planet is too close to its host star and there is a high level of radiation reaching it, it could lose its atmosphere. If there is a planet that has a dense hydrogen atmosphere and is not directly in front of its host star, it would lose most of its primary atmosphere, but it would be able to create a secondary atmosphere. This phenomena is seen in Trappist-1e, as it has been able to develop a secondary atmosphere despite the level of radiation from its star. But how come Trappist-1e has been able to develop a primary atmosphere, but not Trappist-1b, or the others outside the habitable zone? In the early stages of their development, all the planets in the Trappist-1 system have primary atmospheres that are rich in hydrogen and helium, which are captured during their accretion phases. But despite having almost the same amount of these elements, the evolution of the planets all depend on their distance from their host stars, and also the activities of the star during its pre-main sequence phase. When we look at 3D representations of Trappist-1e, we see that the thick atmosphere underwent significant changes as the surface cooled and solidified from its molten state. At this stage, CO2 and water vapors become dominant on the planet while hydrogen escaped into space. During the cooling period of the planet, it was able to form a secondary atmosphere that consists of heavier molecules. These heavier molecules were less susceptible to erosion caused by exposure to stellar winds. When you look at the activities on Trappist-1e in comparison to other planets outside the habitable zone, you will understand why they are there. Let's use the Trappist-1b as an example. The Trappist-1b is closer to the host star than the Trappist-1e. Because of the distance, it has been exposed to ultraviolet rays and high levels of radiation. This high level of radiation did not just strip away lighter molecules like hydrogen. It also stripped the planet of heavier molecules, leaving the planet with almost no atmosphere. Unlike the Trappist-1e, the Trappist-1b did not get a cooling period, so the planet continued to experience atmospheric escape, leaving no room to form a secondary atmosphere. For the Trappist-1e, the interaction between its hydrogen-rich primary atmosphere and its silicate mantle played a crucial role in the formation of its secondary atmosphere. The hydrogen reacted with metal oxides to release water, which accumulated in surface reservoirs. This process helped in the preservation of a significant amount of volatile compounds and helped stabilize the planet's redox balance. This redox balance increases a planet's habitability, but this is not the case for the Trappist-1b because it's in a constant molten state due to exposure to stellar flux. It loses heavy molecules like carbon dioxide. This makes it unable to reserve volatile compounds or even store water, so it can't form a secondary atmosphere. But because Trappist-1e has a secondary atmosphere and may be habitable doesn't mean it's ideal for life yet. The presence of the secondary atmosphere simply means that once its star transitions to a more stable phase, then it is possible that life may begin to form there. However, considering the state of red dwarfs, is this ever going to become a reality?